Okay, guys, lesson 5, antiderivatives and indefinite integrals, basic rules and notations. Okay, so as we start looking at this, we're actually going to start learning how to take antiderivatives and learning some of the rules. So a little bit of vocabulary and definitions. A function capital F. So you're noticing this capital F. They keep using capital F to represent the antiderivative. Antiderivative of a function, lowercase f. So that means if capital F is a derivative, or the antiderivative, excuse me, then the derivative of capital F is equal to the regular function. And the process of finding antiderivative is antidifferentiation. Okay, big words. The family of all antiderivatives yeah, you can read. Why am I reading to you? Because I can't read, obviously. Family of all antiderivatives of a function is the indefinite integral of f with respect to x and is denoted by, and there's an integral sign, f of x. When we talk about indefinite integral, notice it says it is the family of all antiderivatives. Indefinite means you're going to look at that integral sign, and there's not going to be a lower limit and an upper limit. So it's indefinite as in there's going to be multiple answers. We'll talk here in a moment about what that means. Okay? If f, the antiderivative, is any function such that the derivative of the antiderivative equals f, then notice what it says here. The integral is equal to the antiderivative plus c. And that is called your general solution. And c is called the constant of integration. It's some random arbitrary constant. It could be a lot of different things, and we don't know what it is because it could represent a lot of different things. So, the idea that an indefinite integral is going to have multiple different possible answers. And we recognize that by putting a plus c there. So, as we look at example 1, we know that if a function f has an antiderivative, f of x, then there is a family of functions which share the same antiderivatives, and they differ only by a constant plus c. So, okay, state 3 functions, and if you look at this graph here, there's actually 5, but they suggest stating 3 whose derivatives are f of x equals 3x squared. Now, think for a moment. What function would have the derivative 3x squared and looks like this? Just pick one of these, not all, just what function has the derivative 3x squared? And your hint is it looks like this graph here. X cubed, yes? We haven't talked about the rules to get there yet. We're going to do that today. But that's just the basic, okay, if we have x cubed, how do you take the derivative of x cubed? Multiply by the 3 out front, subtract 1 from the exponent, right? So these are all representations here of the antiderivative, okay? So if I say capital F1 of x, one of these could be x cubed and moved up 5, yes? So one option for an antiderivative of 3x squared would be x cubed plus 5. Because what happens when you take the derivative of 5? It's 0, yes? So when you take the derivative of a constant, it goes away. Thus, hopefully you're starting to see why we have multiple answers. So what's another one here? Another one of these functions is x cubed, what? Plus 3? What's the third one?
X cubed.
X cubed. Officially, you could say x cubed plus 0, couldn't you? But it's x cubed. Okay. I know it only said 3, but, I feel like there's 4 on here. Or there's 5 on here. Let's do all 5. What's another one?
X cubed minus 2.8.
So, x cubed minus 2.8. Close. Honestly, it's what I put when I was just doing this until I looked in the answer key to see what options they'd have there. What's a number that is very close to 2.8 that we have a letter that represents? I don't know if you guys are going to come up with this off the top of your head or not. E? What's E? E is 2.7.
Force. It's like a force.
I don't know.
How do you just know this?
Because DC
It's even.
it's just
2.71828.
Okay, there you go. 2.71828. Does that look like about 2.71848 or 28? Sure.
I disagree.
Now, honestly, I'm perfectly fine with you guys saying minus 2.8 because it looks like that too. But just throwing that out there. Now, and what is E? E is a constant. So what's the derivative of E? 0. If it's just E with no x exponent, it's just 0. So, and what's the fifth one here? X to the third minus 5. Okay, so explain the meaning of the plus C on your functions. In other words, the plus 5, the plus 3, the minus E, the minus 5, the plus 0, if you will. Okay, it's a vertical translation, yes. It's taking that graph up or down however many. The key is, though, it's also forming the family of antiderivatives, right? Because 3x squared, all 5 of these that I just wrote would have the derivative 3x squared. Okay, so this is what I'm leading you into the idea of an indefinite integral. That when we see indefinite integrals, we're not going to know what number goes there, so we're going to tack on a plus C. Okay? And so, one thing you might want to put here is that the graph is translated up or down C. Okay. And the other thing is it also helps form the family of all the antiderivatives here. I don't know how I want to write that, but just family of antiderivatives of f of x equals 3x squared. Okay, so both are key things to notice. Physically, yes, the C is making that translation, but it's the family of antiderivatives. You can put any constant in there and it's going to work. Now, when I asked you guys for the what would be the antiderivative of 3x squared, Jacob was able to come up with it, and I think you guys followed in with him and it made sense to you. Okay, so we're going to look down at example 2, and we're going to talk, and if you notice in the directions, it says, given each derivative below, find the general antiderivative by just guess and check. We're going to talk about rules as the day goes on, but we're also, more than anything here, we're going to kind of discover some rules. Okay? So, if the derivative is 2x, thoughts on, I can either say it's one of two ways, what the antiderivative would be or what the original function would be. Does x squared make sense? Because you're taking that 2 and putting it back in the power, aren't you, essentially? Now, officially, to give the general antiderivative, I need to tack something else on there. Plus C. Okay? So every indefinite, unless you have number values to plug in, which that's a lesson for another day, you always want a plus C on there. It will cost you points with me. It will cost you points on AP. So that C could be anything, but you want it on there. Okay? Okay. Thoughts on B? I like it. Does it make sense? One-third t to the third. How do you check yourself? You take the derivative, yes? Remember to take the derivative. It's 3 times a third. And 3 times a third is going to be 1, right? And then subtract 1 from the power, and that's 2. So you're at t squared. Plus c is not going to let me get away with forgetting it. Not to say that I'm not guilty of forgetting it at times, too. Okay. Are you starting to see any type of rule here? Now, in the next one, essentially we're working on figuring out the power rule right here with these top row examples. Okay. The derivative power rule is what you guys know to move the coefficient out front, subtract 1 from the coefficient. We're working backwards now. Okay. Before you do this, what would you have to do to take the derivative of this? We'd rewrite it with a negative exponent. So what am I going to have you do before you do an antiderivative of it? Rewrite it with a negative exponent. There we go. What happened to both of our powers on these past two? They went up by 1, yes? Every time we added 1 to the power. Derivatives, you subtract 1 from the power. What are we doing with antiderivatives? We are adding 1 to the power. Now, here, we added 1 to the power, and then what else did we have to do? This 3, we basically had you take the new power and divide by it. Okay, and here, I wrote this as 1/3 t cubed because that's what was said. This could also be written as t cubed divided by 3. So you're adding 1 to the power and dividing by it. Get that on there so I don't get in trouble. Does that work here? If you add 1 to the power, it becomes 2. And then what else would you have had to do? Divide by 2 would cancel that, right? So use those thoughts to think about this. If we add 1 to the power, what are we going to be at? -1. And then if you divide by the new power, what are you dividing by? New power is -1. So if you divide by -1, it's the same thing as multiplying by -1, if you will. Okay? If you'd rather, I don't know, maybe for right now I should say divide by -1. Let me do that for a moment. Now, what does this clean up to be? Well, negative x and negative first, or -1 over x. I'm running out of room. Don't forget, plus c. All of those, that's probably bad form for me to write all of those equal to each other like that, because there really should be plus c's in there. Now, while our brains are on this length, let's do e next. You don't like those fractions, Ethan?
I love them.
Huh?
I said I love them.
You love them? Okay, we'll talk D and F in a moment. D and F are more special cases. But E, it's a power, right? So this power rule we've been working to figure out. Well, got any guesses for me?
E over 21x is 7/4 plus c.
I like it for a final answer. As everyone else is saying, what? Or at least several other people are saying, what? Okay, so what do we do with the power? We add 1. What do you add to 3/4 when you add 1? You're adding 4/4, right? 3/4 and 1. So 3/4 and 4/4 is going to make this x to the 7/4. Are you at least convinced there? Now, I'm going to write this real ugly for a moment. I would never write this other than we're learning right now. There's already a 2/3 out front, yes? What was I indicating that we have to do? Divide by the new power. What's the new power? 7/4. That's ugly. I would never do that other than it's day 1. How do you do 2/3 divide by 7/4? We multiply by the reciprocal. So really, what we're going to think is this is, try again. There's a 2/3 out there, yes? And instead of dividing by 7/4, you're going to be multiplying by 4/7. Okay? So when you're dividing by a fraction, you're multiplying by the reciprocal. So I'm going to be doing 2/3 times 4/7. And 2/3 times 4/7 is the magical 8/21 that Miles mentioned. So this is 8/21 x to the 7/4 plus c. You'll like it once you get used to it, I promise. It's an easy rule. Add 1 to the power, divide by the new power. Okay? Now, D and F, I feel like are kind of randomly thrown in here. Okay, so first of all, df d theta. That is the derivative of f with respect to theta, yes? So you could also think of this is f prime of theta is equal to cosine theta. That's what they're saying there. I want to know what f of theta is. This is just a flat-out rule you have to know. Use what you know about derivatives, obviously. What's your guess?
Sine theta.
Sine theta? And again, I'm the one that's almost always checking myself, especially when it comes to trig rules, because we know derivatives, yes? Now we've got to turn them around. And this is where I check myself because I know my derivatives better. What's the derivative of sine theta? Cosine theta. So does it make sense? Yes. And what else did you put on your answer?
Yes.
Plus c. Okay. So f prime is e to the x. Thoughts on what the original function is? What's your guess?
I would say e to the x plus c.
Because what's the derivative of e to the x?
Itself.
Itself. So what's the antiderivative of e to the x? Itself. Okay. So some of these, like e to the x, cosine, those are rules you're just going to have to know. Take what you know about derivatives and put it into play. Some of these power rules were learning rules. Okay, it's okay. How do we reverse that? Now, let's see. Okay, so top of the next page, a little bit of information. The expression, I usually read it as the integral of f of x dx, but it is also can be read as the antiderivative of f of x dx or of f with respect to x. The differential dx is there to identify x as a variable of integration. What are we integrating with respect to? Okay. The term indefinite integral is a synonym for antiderivative. Okay, that is a synonym for antiderivative. Notations for antiderivatives. We're going to talk about several of these as we go through things, but the idea that dy dx equals f of x or dy equals f of x dx. We're going to talk about those as we go through more. Let's see. The operation of finding all solutions of this equation is called antidifferentiation or indefinite integration, denoted by sign. Fill in a couple of vocabulary pieces here. We've already talked about some of these, but dx here represents your variable of integration. Integration. Okay. The plus c is your constant or constant of integration. Okay. Your original f of x is one way to talk about it, is your integrand. It's what you are integrating. So integrand is a good way to talk about it. And then f of x is going to be your antiderivative. Or capital F of x, that is, sorry. Okay, your antiderivative. Now, I'm not doing the notes out of order, but we're going to flip to page 366 for a moment. You see a page of
Basic integration.
Basic integration rules. Do you have enough time? I guess we'll find out. I guess I have you fifth hour, don't I? Yeah. So, okay, you got a page of basic integration rules, right? On the left, what's on the left? My derivative rules. Okay, things like the derivative of a constant. We've already talked about that today. It's 0. You do the derivative of kx, like the derivative of 2x. That's just 2. This one talks about using a chain rule, some things like this, okay? Your trig rules are all listed right here, so there's your review. You don't even have to pull out your old notebook. Well, yet. I don't know. There was one in homework. I needed the old notebook. Well, I thought about it, but yeah. So, now, then you've got a couple special cases down here with natural logs. Over here are your integration, okay? So, the idea of the integral of a constant. Well, we're going up powers now, right? So here, the derivative of, say, 2x was 2. Here, the integral of 2 is going to be 2x. That's a basic rule there. The idea that a constant can be pulled out front, we'll talk about some of these examples when we get to them. You can split up adding and subtracting. Right here is what I just taught you. That's what we kind of discovered with the power rule. So right here, this is saying the integral of x raised to some power n. Notice what it is. It's x to the n plus 1, so you're adding 1 to the power, and then you're dividing by that new power n plus 1. Okay? Notice it just talks about n cannot equal -1 because then that would give us a 0 in the denominator. Okay? All of these plus c is tagged along. With the trig rules, they're just opposite of each other, aren't they? Okay, so again, you have to think careful. The integral of cosine and sine, we just talked about this one. Integral of sine. Well, this is where we're going to have to say negative cosine, because what happened over here? The derivative of cosine is negative, so now we're reversing it. So, they're all listed here, right? Refer to this page as you need it. We'll talk about several of them as we go, okay? I know the integral of a to the x dx, remember that's when your base is a number. I think that one came up in homework once. I don't think it came up in notes, but I think it came up in homework when I was doing that last night. The integral of 1 over x being equaling to ln x. This is reversing the rule, right? I know it came up in homework a couple of times. Whether it came up in notes or not, I can't remember exactly. But several of these came up, so we're going to work with them. Now, oops, wait, I'm going the wrong way. So now you go back to where you were, and let's look at example 3. When integrating, think before you work. Practice will help you discover many tricks and techniques that make the integration rules fit your problem. So some of these, as you know, you get used to them, will be very obvious. Some of them, the more we practice them, the better off they'll be. Okay? So, trick number 1, the integral of 5e to the t plus 1 over cosine squared dt. First of all, officially, if I'm going to be nitpicky, that should be in parentheses there, just to indicate that it's all in the integral. But notice trick 1 is to rewrite it. And when we talk about rewriting it, and I'm not even talking about rewriting it as 2 integrals, 5e to the t, we're going to be able to do the integral of that just fine. The integral of 1 over cosine squared t, that in the denominator makes me pause and say, oh, yuck, I'm not sure what I'm going to do with that. So how can I rewrite that one so that cosine squared is not in the denominator? Thoughts? What's another way to say 1 over cosine squared? Okay, so cosine to the negative 2 takes out the denominator, but then I have a negative exponent, which isn't going to be.
Could this be like cosecant? No, secant.
That's more the direction I'd prefer to go in this case. What is the reciprocal function of cosine? That's the secant. I was cringing when he said cosecant, but it was getting us there. No, you're fine. It was getting us there.
Well, when I think of it, I think of CSC, SEC, and COT. I always forget the order, and when I stack them up, that's when I can figure it out.
See, I always remember opposite first letters. So,
Yeah.
like, cosine does not go with cosecant. It goes with the other one then. So, but, okay. Are we okay with that rewrite now that you process it? All I did is I just rewrote it in a different form. Here in a moment, probably doesn't look it, but it's actually a very easy problem now once you know your integrals. Or your So, okay. Integral of 5e to the t. What would be the integral of e to the t? E to the t. Now, officially, if you look at your rules, one of the rules is you can pull a constant out front. And so if I were to rewrite this as 5 times the integral e to the t, what am I saying there? That's going to be 5e to the t, yes? Because the integral of e to the t is going to be e to the t. So integral of 5e to the t, when there's that constant out in front, it just gets to say. So 5e to the t plus integral of secant squared. This is 1. Think about your derivative rules and reverse them. I know, your derivative rules are rusty. So it's on that other page.
Tangent.
The derivative of tangent is secant squared. So the integral or antiderivative of secant squared is tangent. And this is tangent t. So the integral or antiderivative is 5e to the t plus tangent t plus c.
Is this like actually how you do integrals?
I mean, we're just talking about indefinite ones. I believe in the next lessons where we get to definite ones. So like how to then evaluate if there's lower and upper limits. But we've got to make sure we know how to find these first. Okay, so sometimes you have to rewrite things, put things in a different form. Sometimes, like on number 2, you really don't want to try and do the integral in this form. You can do the derivative in this form, not too bad, but you don't want to try and do the integral in this form, or the antiderivative. So what do you know about 3x minus 1 quantity squared? What do you know about 3x minus 1 squared? It can become
9x squared
9x squared
minus 30x. Oh, 6. Yeah.
minus 6x plus 1.
Oh wait, it's the.
We're rusty, aren't we?
Not the fourth.
In order to expand 3x minus 1 quantity squared, we distributed, we FOILed, right? You can do that in your head. You just have to not be rusty, right? Okay. Now, the nice thing is, once you multiply out or distribute, now we just have 3 different terms to integrate. Okay? So, integral of 9x squared. Basic power rule. It's just x to some power, so basic power rule. Okay, we're going to add 1 to the power, and I'm going to, well, okay, I'll leave it right here. Add 1 to the power, it's going to be x to the third. The 9 stays out front, and then what do we also have to do? Divide by 3. Will that clean up in a moment? Yes, you will clean that up. As you get great at this, you would have never written it in this form. Okay? Minus, what about 6x? We're going to add 1 to the power, so it's 6x squared, and divide by that new power, too. Plus, what's the integral of 1? 1x, x. Okay, now, do clean it up. Don't leave it in that form. Three x cubed minus 3x squared plus x plus c. And stop me if you're struggling with some of these. Let me explain them differently if I need to, but I'm finding one thing I don't like about this curriculum as much. All the rules are thrown together at once. The advantage of last year, my Saxon book, it was baby steps. Here I'm like, okay, we're doing everything at once today. So I'm trying to keep it slow. Okay, another trick. This is one that I've seen a lot of my students get caught by on AP test, where they'll say, okay, integrate this. Take this integral or antiderivative. And then no one knows what to do. Okay, so this is a good rule to see from the beginning. But the suggestion here is to separate the fractions. In other words, instead of having one big fraction that has variables on top and variables on bottom, I don't really know what to do with it, we can break this up and write it as 3 smaller fractions. And when we write it as 3 smaller fractions, they'll actually also simplify. Because what is x to the second divided by x to the fifth? X to the negative third plus, what is 4x divided by x to the fifth? (4x) to the negative fourth, because you keep the 4 up top, and then 1 minus 5 makes it negative 4. Plus, what is 5 divided by x to the fifth? 5x to the negative fifth. And officially, yes, you could say 5 over x to the fifth, but I'm trying to set us up to take the antiderivatives here, aren't I?
Are you allowed to separate like the top from the bottom? I feel like we do that.
I don't know what you mean.
The integral of like the top and then the integral of the bottom.
No, you cannot do that.
Did we
Not
do
with
that for
integrals.
something like derivative?
We did that with L'Hopital's rule.
Oh,
Derivatives and L'Hopital's rule.
is this not the same thing?
Definitely not. Definitely not. Okay, have you started? We'll have to review L'Hopital's. Okay, integral of x to the negative third. It's going to be x to the negative 2 divided by negative 2. Add 1 to the power, divide by the new power. Plus 4x to the negative third divided by negative 3. Plus 5x to the negative 4 divided by negative 4. Now, I would not leave it like that. First of all, those negatives I would change into minus signs rather than having negatives on all my denominators. Negative exponents, I don't know. In calculus, I see it go both ways. I could see negative exponents being left. I also see negative exponents being pulled back down to the denominator. Be comfortable with either way, right? So if I get rid of the negative exponents, I'm going to say negative 1 over 2x squared minus 4 over 3x cubed minus 5 over 4x to the fourth plus c. And when you're ready, trick number 4. Notice it says multiple options. We're going to combine a couple of the options we just did. What should we do first? Okay. Rewrite in terms of looking at the numerator. What do you know about x minus 3 quantity squared? Can that expand to be x squared minus 6x plus 9? What do you know about the square root of x? It's x to the 1/2. So we use the multiply or distribute option. Is that bugging anyone else here? It says multiple or distribute. My brain should say multiply, but okay. Now we can use the idea to one denominator, separate this into 3 separate fractions. Fun fractions at that, aren't they? What's x squared divided by x to the 1/2? X to the 3/2 minus 6x divided by x to the 1/2. 6x to the 1/2, is that what we said? Plus, what about 9 divided by x to the 1/2? I mean, it's 9 over x to the 1/2, but in prepping for antiderivative, I brought that x to the negative 1/2 up. Okay. And now, I'm ready to integrate. Okay. What do you think about x to the 3/2? Add 1 to the power, and what is 3/2 plus 1? 5/2. And then what? Divide by 5/2. Now, how do you want me to write that? Do you want me to write it as divide by 5/2 the first time through? Because what am I then going to immediately switch it to? Dividing by 5/2 is multiplying by 2/5. Is it too soon, or can I go ahead and do that? Because ideally what you guys will get into the habit of is this is 2/5 x to the 5 halves. Okay, that's the habit you'll need to get into. If it's too soon, then by all means, it's x to the 5 halves divided by 5 halves. Yes?
Is it 1/3? Where did you get 5 halves from?
Because I added 1 to the power. 3 halves plus 1.
Oh, shoot. Yeah.
So 3 halves plus 2 halves
Yeah.
is 5 halves. Is that what you need to hear?
Yeah. That
Okay.
was still.
Okay. No, there's a lot going on today. In my brain, this is an easy lesson, but yet it's easy to me. It's a lot new to you guys all at once. So, okay, we're ready for the next one? There's already a 6 out front, yes? And then, let's see, x to the 1/2. When you add 1 to the 1/2, it's going to become 3 halves, right? 1/2 plus 2 halves is 3 halves. And then when you divide by 3 halves, what are we doing? Multiplying by 2/3. So you're going to be multiplying 6 by 2/3. Do that now or do it later? Yes. Oh, you're saying that's what it multiplies to be. Yes, it will be 4, and I'll write that in my next step. And plus, okay, 9x to the 1/2. There's a 9. Add 1 to the power. I'm now at positive 1/2. Dividing by 1/2 is multiplying by 2/1, which is 2. And then at this point, it's cleanup if you've got all that. Okay, 2/5 x to the 5 halves minus 4x to the 3 halves plus 18x to the 1/2 plus c. Fun stuff, right? Okay. Next page when you're ready. How often do you get to do matching in calculus?
I don't know, but
Oh my
I kind of like
goodness.
it. Yay!
I kind of like it, although it can be a little tricky at times too. The first group is the easiest, of course. Okay. We'll go group by group here. So in the first group, the original function is in the first column. The antiderivative is in the second column. Okay? So I'm going to say, okay, this one right here. Question 1, so to speak. Take a moment before you say anything out loud. Has everyone had a chance to give their guess? In their head, at least? What do you think? C? And here's the deal. You know you're looking for something that is x cubed, right? Because the highest power is x squared, so you're going up from there. So that takes it to ABC. Okay. If you pinpoint, you can look at all the terms, but like here I see a -5. That means over here I need to see a -5x. Take the derivative of C. Does it match up with the first one, right? Lots of different ways you can look at this. Okay? What about the second one? A? Are we all finding them kind of in our own way? What about the next one? So she says that one is D. Well, process of elimination. I'll fill in the last one. Okay? And again, look at the things. Like this last one, 6x squared, I need to go up to an x cubed. So I've got one of these three but I also need it to be a 6 out front, so that takes it to B or C, you know, things like that. Look at them. Okay. Now, on the second set, notice it says match the integral to antiderivative. It does define x to be greater than 3, and that's just because otherwise your denominator, you'd have some 0 denominators, and that's not okay. So x has to be greater than 3. Okay. Notice, I'm trying to decide how I want to teach this here, but what do you notice all of my antiderivatives are here? They're all natural log, yes? And if we go back to derivative rules we learned, okay, so this is what, you know, we learned, seems like eons ago right now, that the derivative of the natural log of x is equal to 1 over x, right? Now, we're reversing that, right? And so if we're reversing that, we're reversing it to the idea that the integral of 1 over x dx is going to be equal to the natural log of x, and of course plus c. None of them are that clean though, are they? And you know when you take derivatives, there's this chain rule thing. Well, when you go backwards and do antiderivatives, that chain rule still has to be there somewhere. Okay? I always think of it as compensating for the chain rule. Are you seeing where I'm going with this?
No.
No?
So
Now, go ahead.
Never mind. That was, yeah.
Thoughts on what the first one matches up with? Okay. Yeah. Now, why would you pick G? I mean, it's multiple choice here, matching, but okay. And here's the deal: this denominator is x. None of these others have things, you know, plus and minus here, right? But look at this one with me, and I'm just doing some side work. If we do the derivative of the natural log of 2x, well, okay, see how this works? The derivative of the natural log of something is 1 over something times the derivative of something. What's the derivative of 2x? 2. You see it now? I think if I do some of this working the derivatives, you'll start to see it. Okay? You can really shortcut this if you want. What's the second one have to go with? Uh-huh. And there's a power connection you can make here about what's in the derivative. Now, do you want some proof of E? If we're doing the derivative of natural log of 2x minus 6. Derivative of natural log of something is 1 over something times the derivative of something. What's the derivative of 2x minus 6? 2. Does that really work? Yes, because what do you know about 2x minus 6? That's 2 times x minus 3, isn't it? So 2's cancel, and you have the 1 over x minus 3.
How do we work this like backwards? Or you just don't really?
It's more of a I don't know that I'm ready to. It's more of a, I mean, it is somewhat to an extent a guess and check thing. Especially with the amount of canceling we're seeing here. That's the thing. Because it's a little bit harder with, oh, that was 2x minus 6, this is x minus 3. I don't know, it's a discussion for another day, I think, at this point. Okay. What's the third one pair up with?
H.
H, which is the x squared one, right? And then that means the last one pairs up with F, which is the x cubed one. With each of those, again, you can work them forwards to do some checking. And we're kind of more at the guess and check stage than anything. Okay? Notice she didn't give any of these and say, okay, what are they? Now, in homework, there were a few that I was like, ooh, not sure if we're ready for this, but we'll make it happen. So, tomorrow, actually, what I'll probably have you start off doing is seeing if you can figure these out. I mean, you can narrow it down. There's 2 and 2, right? But it's figuring out which is which. So, we'll start there tomorrow, and then we'll solve some differential equations. And then I know I'm going to do a homework example or 2 with you also as part of the notes because she threw something in the homework that she didn't teach in the notes. So I was like, but just means I'll do a homework example as part of the notes is what it means. So we'll pick up there tomorrow.